when he began to predict spectra, he was actually able to correctly make predictions and get the actual spectra or the pictures, but it only worked for some of the lighter elements. As he got into heavier elements, it didn't necessarily work. So we had to come up with something new, or at least modify what Niels Bohr had stated. Here's where we come up with the Schrödinger equation. Now, the Schrödinger equation, and we're getting into a little bit of physics here. Am I still sharing? No, I'm sharing my paper. Let me share the, here we go. This is what I want to share. So remember way back when I mentioned on Monday that we now know that there's a dual nature to light, that it behaves not just as a wave, but it also behaves as a particle. Well, the Schrödinger wave equation took into account the dual nature of light. And light is what really helped us understand how atoms are put together, at least contributing to our current understanding of how atoms are put together. The Schrödinger equation, and I was going to write it out, it's a very complex, advanced equation. We won't be using it to solve for anything, but what we will be talking about it is that the important part of it that you'll see about a quiz is right here. It's the equation that basically put together the two natures of light, that light behaves as both as a particle and it behaves as a wave. So the particle part was, emitting photons of light, packages of energy, so to speak. And the wave nature was that this light corresponded to wavelengths seen on the electromagnetic spectrum. So what the usefulness of the Schrödinger equation for us was that it was going to allow us to make predictions, at least based on the probability of finding an electron in an area of space. In other words, if we accepted that electrons behave like particles, could we predict where they might be? And the answer is yes, using the Schrödinger equation. The Schrödinger equation, and I'm skipping ahead a couple of slides because I'm looking for a particular slide here. Let me go back. The Schrödinger equation, what it allowed us to do, like I mentioned, was to predict the probability of where you might find an electron. So using the Schrödinger equation, there we go. So what the Schrödinger equation did was it allowed scientists to predict the probable location of an electron. And we couldn't predict the exact location, but we could predict the probable equation or probable location. And the reason that we say the probable location is because of something called the Heisenberg principle. How many of you watched Breaking Bad? I won't judge you. I watched Breaking Bad. If you watched Breaking Bad, you remember Walter White's alter ego of Heisenberg. And I thought it was such a clever choice for his alter ego because of the relationship to the Heisenberg principle. And what the Heisenberg principle says is that one cannot ever the exact location of an electron. You can only predict where it's likely to be. Not even likely. You can only predict where it might be located. So the Schrödinger equation took into account the Heisenberg principle that even if we did this fancy math, we'll never know exactly the location and the momentum, because we are talking a little physics here, the exact position and the way that something is moving at any particular time. All we can do is predict what it might be. So when Walter White chose Heisenberg as his alter ego, what he was saying is that you can never really know where I am. You can only guess. Very clever, Walter White. When they solved the Heisenberg equation, when they solved the Schrödinger equation, this gave rise to the probable shapes of what they thought was a three-dimensional area of where an electron might be located. So one of the three-dimensional shapes was not a circle, but a sphere. So like a ball, if you will, we're thinking three-dimensionally. Another one was something that looked very lobed. So we got something that was lobed like this, on top with lobes like that, and then lobes like this. So on an X plane, a Y plane, and a Z plane. So we got these lobed kind of shapes. And so what the Schrödinger equation helped us do was to figure out that the area where we can find electrons is not exactly an orbit or a circular path. Instead, these energy levels are three-dimensional shapes. They're not orbits, they are three-dimensional shapes. And you can find these three-dimensional shapes on page 298 of your textbook. And I thought I had a picture. Yes, I do. Or starting on slide number 48. And so these three-dimensional shapes were also, what's the word I want to use? They were also, my mind just went blank. These three-dimensional shapes were also related to the distance from the nucleus and by size. So for example, we knew that there was small spheres that got bigger. And so they called them the 1s, the 2s, and the 3s. And they were actually nested inside of each other. And then we had, these lobes, which we call the P shells, but we call them the PX, the PY, and the PZ. We also know that there were 3 P shells that were the same shape, just bigger. So these shapes, we don't call them orbits, we call them orbitals. We don't call them orbits, we call them orbitals. And an orbital, this is a three-dimensional area where you are likely to find an electron? It's a three-dimensional area of where you're likely to find an electron. So what we know now about the cloud, and again, I'm just hitting the highlights of the video that I hope you guys watched. What we now know about the cloud is that it's much more complicated than just, these circular orbits. There is an energy level, which is encompassed by another energy level, which contains another energy level, which then has another energy level around it. And so we have these patterns of energy levels that just repeat one over the other. So we have principal energy levels, which Bohr was right about. So we have like principal energy level number 1, number 2, number 3, and number 4. But within every principal energy level, we also have sublevels. And so we have the same number of sublevels, which corresponds to the principal energy level number. So this represents a sublevel. Sublevel is the same thing as an orbital. So this number here is a principal energy level, and the S represents a sublevel. So the one principal energy level has a single sublevel. Principal energy level number 2 has 2 sublevels. Principal energy number 3 has 3 sublevels. You're getting the idea. Principal energy level number 4 has 4 sublevels. Here's what we know about sublevels, or we can call them orbitals. Here's what we know about them. We know their shapes. Okay, we know their shapes. So if you're looking again on slide number 48, which is I'm going to share with you right now, here's what we know about sublevels. We know that all S sublevels are shaped like a sphere. The only difference is that as the principal energy level number increases, so as we go from 1s to 2s to 3s, they keep the same shape, they simply get larger. It takes a lot of energy to exist in the larger sublevels. So 3s is a higher energy level than, let's say, 1s. In real life, if you want to think of it that way, these are nested one inside of each other. So the 3s bubble holds inside of it the 2s and the 1s, because these are three-dimensional shapes. We know the shape of the P levels, as I mentioned before. They're lobed. This one shows them kind of like two little circles, but they're more lobed than that. And the three of them, they're on 3 different three-dimensional planes. So this one's on the X plane, this one's on the Y plane, and this one is on the Z plane. So they're often referred to as the PX, the PY, and the PZ. The first energy level where a p orbital exists is in the second principal energy level. So you'll only see this. So the lowest p levels you'll see are 2 p's. So 2px, 2pz, 2pz. The 3 p's are the same shape. The 4 p's are the same shape. They just get bigger. I'm going to advance one more slide here. The d orbitals, 4 of them are lobed, and one of them has this kind of a lobe and then a donut shape. And so when we look at them, what I want you to remember is they look mostly like a four-leafed clover, except this crazy one, but they're located on different planes. So if you look at them on this one, you have two of them on the X, two of them on the Y plane. So that's why this is called the X squared, Y squared. The first energy level to have a D set of orbitals is the third principal energy level. So this diagram represents the lowest energy 3D levels. They get their names again by where you find the orbitals. Remember, these are areas where you're likely to find an electron. I'm not going to ask you to sketch these out, but what you should have is a general idea of what their shape is. So what I'm writing down is know the general shape of these orbitals. See slide number 48 and 49. These pictures are on page 298. So if you want to know what am I writing down, what you should know about sublevels is know their general shape. And then you should also know how electrons occupy these orbitals, which is what I'm going to talk about now. How do electrons occupy these orbitals? Well, we'll take the simplest electron, or the simplest element, hydrogen, which has one electron only. And then we'll compare that to helium, which has two electrons. When we occupy orbitals according to their energy requirements. Electrons occupy lowest energy levels first. Electrons also spread out before they double up. And I'll show you what that means. And lastly, any sublevel can occupy or can hold 0, 1, or 2 electrons. So the max number of electrons you can put in a sublevel is 2. So we'll start with hydrogen, and it's 1 electron. If we try to diagram or write out where that electron is occupying or how the electron cloud is filled, the 1 electron is going to go into the first principal, energy level first, and it's going to occupy the s orbital, or you can call it the s sublevel. So what that means is we're in the first principal energy level, we're in the first sublevel, and then I put a little 1 at the top like an exponent to indicate that's my 1 electron. If I do the same for helium, which has 2 electrons, 1, S, 2. So this number 1 here represents the principal energy level. This S represents the orbital that we're in, and this right here represents the number of electrons that are located in that principal energy level that are located in that orbital. So if I was looking at this, I would know that I was talking about helium because I'm talking about a total of 2 electrons. And the element that has 2 electrons is helium. This is basically the address of where those electrons are located. They're both located in the 1s orbital. We kind of used to indicate that, when we would draw out, hydrogen like this. Okay, or helium like this. This is a very simple representation of what was going on. So writing it out this way is another way to represent where those electrons are located. This method is referred to, and I think I'm running out of room, but that's referred to as the electron configuration of an element. It's literally the address of where those electrons are located. Give me a number 1 in the chat window when I can move on to the next page, because I know there's a lot of detail on this one. All right, good. Y'all are keeping up with me. All right. So writing electron configurations takes a little practice. But one of the things that you need to know is the order of filling the principal energy levels and their shells. I don't have this information on a slide, but I do have this in your book. You can find this in your book at the bottom of page, I just saw it. Where did I see it? Oh, at the bottom of page 299 in your text. And then I have a diagram which is on the next page, figure 7-24 on page 300, or slide number 62. For those of you following along in the slideshow. But here is the order. You fill out 1s first, then, try that again. 1s requires less energy than 2s. These two are actually at the same energy level, but you fill this one first, and then the 3s, 3p, 4s, um, 3d, 4p, 5s, so on and so forth. Because of the rule that you always fill lowest energy levels first. So I'll kind of pass out this rule and we'll use it and I'll relate it to the diagram on page 300 or on page 62. So let's take, for example, we'll take somebody like beryllium. What number is beryllium on the periodic table? Tell me out loud. What number is beryllium on the periodic table?
4.
4. So how many electrons does it have, Bob?
4.
Okay, 4 electrons. So we'll write out the electron configuration of those 4 electrons. They'll start out in 1s. Remember, our rule is that this can hold a maximum of 2. Now we have 2 more to worry about, so we're going to put them in 2s, 2. These little exponents up here, if you add them up, that tells you how many electrons you're talking about. So you can know from the configuration what element you're talking about by simply adding up what looks like those little exponents. We'll try one a little more complicated. Let's try nitrogen. What number is nitrogen on your periodic table?
7.
7. So we're talking about 7 electrons. So when we figure out their configuration, 2 will go into the first principal energy level. Then we move to the next higher level. 2 will go in there. We've accounted for 4 of them. The next set of orbitals, because we're not moving principal energy levels, but it'll be the 2p. Now I only have 3 that I need to worry about. So I put a 2p3 there. So again, I can tell that I'm talking about nitrogen if I add up 3 plus 2 plus 2. That is the 7 electrons I'm talking about.
So, Ms. Weir, can I ask a real quick question?
Sure.
So when we talk about the placement in the orbitals, they don't, you were talking about earlier how the electrons move when they get photon energy and all that, they don't change orbitals, or they do change orbitals?
They change principal energy levels.
But they would stay within their orbital, just in different positions?
No, if you go to a different energy level, you go to the orbitals in that energy level.
Oh, okay.
The one thing is that all elements, even though we're not writing anything beyond 2s, the 2p, the 3s, the 3p, and the 4s, they all exist. They're just empty. So even after this, you have all of the orbitals that I have written on this line. They still exist. They're just empty. So when those electrons were being energized, they were jumping beyond what is called their ground state. We'll do one more and I'll explain a little more about ground state. Neon is number 10. Neon's number 10. So if I have to accommodate 10 electrons, okay, the first two go in the first principal energy level. The second two go in the second principal energy level in the s orbital. But then I also have the p. So now I have accounted for 4 of them. Now remember that I have 3 different p orbitals. So I can accommodate up to 6 total electrons if I kind of put them all together. So if I do this, now I've accounted for all 10 of those electrons. I mentioned, Bob, the ground state. That's where electrons reside when they are not energized. So in other words, this is where they hang out all the time. I'm going to write in red so that I can kind of explain the 3s and the 3p and the 4s and the 3d and the 4p and the 5s, and I'm copying that from up here. They exist, but they are empty. They exist, but they are empty. The only time that they would have any electrons in them is if I put this in a glass tube. If I put neon gas in a glass tube and I pass electricity through it, Bob, then these electrons start moving up into the higher levels. And then when I take that electricity away, they start falling back down to their ground state. And when they do that, they emit light. And that's what I call a neon light. And I use that technology to make things like Budweiser signs to hang up in bars. That's the only example I could think of a neon light. Isn't that terrible?
Okay, because I gotten a little lost there.
Okay. So those other ones, they exist. They're just empty. They're just empty. Okay. So something that I would expect you to do is to be able to write out the electron configuration for easily elements 1 through 20 in their ground state. I would expect you to be able to do that. I would also expect you to be able to interpret the electron configuration. So for example, let's say I had this, and I asked you, what element are we talking about? How could you tell what element that was? What do you need to do?
Count up the electrons.
Yeah, just add up all these superscripts, add them up, and that tells you how many electrons that you're talking about. So what is that number? 2 plus 2 plus 6 plus 1. We have 11 electrons. What element is that? Sodium. What if we had something like this? Who is that?
Silicon.
14, yeah, 14 electrons is silicon. You get the idea. Now I'll show you some shorthand, what we call the noble gas configuration. We'll start with helium because he's the simplest. We'll start with helium, he's the simplest, but then we'll move on to neon. Who's the next noble gas?
Oxygen.
Nope, try again. Noble gas.
Oh, neon.
After neon is
Argon.
argon.
And then Superman's home planet of Krypton.
I'll use these three. But yes, you get the idea. Now, what we said about noble gases, with the exception of helium, way back when we were learning about these guys, is we said that the reason that they're called noble gases is because they don't react with anyone else. In other words, they have full valence shells. Remember that discussion? They have full valence shells. Helium only has 2 in its outermost shell. I mean, it only has 2 altogether. But then if we drew a picture of neon, we would show that it has 8 valence electrons. If we did with argon, we'd also show that it has 8 valence electrons. Well, you can tell that from its electron configuration. If I look at argon, this is the outermost, that is the outermost shell. How many electrons are in its outermost shell? 8. Look at the outermost energy level here. It's the 2s. So everybody in the 2, how many do I have there? Well, with 8. We said that neon and oxygen, they both satisfy the octet rule. Helium, because it's such a small element, it satisfies the duet rule. And you can tell that from their electron configurations. Every element is trying to achieve the configuration of a noble gas. That's why elements lose and gain electrons. They're trying to achieve the noble gas configuration. So elements lose and gain electrons to obtain the noble gas configuration. That's why they do that. So for example, let's take into account one that we've already done, sodium. Its configuration is 1s2, 2s2, 2p6, 3s1. When I look at sodium, it has 1 valence electron. We know from its position on the chart that it is easier for sodium to lose its 1 valence electron than try to gain an additional 7 in order to satisfy the octet rule. And we know from its position on its chart that sodium forms a +1 cation. Well, I can write the electron configuration of sodium because it looks just like this. Whereas this guy has 11 electrons, this guy only has 10. By the way, whose electron configuration is this? Sodium ion has the same electron configuration as which noble gas?
Neon.
Neon. And I just mentioned that elements try to lose or gain electrons in order to obtain a noble gas configuration. We say that sodium ion is isoelectric to neon because it has obtained its noble gas configuration. I'll give you another example. Let's look at oxygen, number 8. From its position on its chart, who is oxygen trying to be like? What noble gas is oxygen trying to be like? Who's the closest noble gas? Tell me out loud. And if you don't have your periodic table handy, well, this is going to be hard. So from its position on the periodic table, who's oxygen trying to be like?
Can it go up or down either way?
It's going to go to the closest one.
So that would be neon?
It's trying to be like neon. Whenever oxygen forms an ion, what's the symbol for oxygen as an ion? Does it lose or gain electrons?
Loses.
Nope.
Oh, sorry. I looked at the wrong one.
You might want to say
Gain
loses because it has that minus on there, but remember when we write them up here, it means that it has gained 2 negative charges or gained 2 electrons. So if I write out the configuration of oxygen, 1s2, 2s, oops, 2, 2p, oh my gosh, 2p6. So now if I look here, I've gotten the octet rule. That's the same configuration as who? Same configuration as neon again. So both sodium element and oxygen as an element, they're both trying to obtain the noble gas configuration of the closest noble gas, which in both of these just happens to be who? Neon. So we can say that sodium as an ion and oxygen as an ion, they are isoelectric to neon. Isn't that crazy? Last thing, and then I'll let your brains rest. Because noble gases have satisfied either the octet or the duet rule, sometimes we use their configuration, we abbreviate it in order to write the configurations of other elements. So like, for example, another way that we can write something like sodium is we can write in brackets like this, neon 3s1. And the same thing with oxygen. We can use in brackets, the closest one for it would be helium. We can use the abbreviation of the nearest noble gas. So that would stand for 1s2. I don't think it saves you much on oxygen, but on the neon one, it would save you writing out 1s2, 2s2, 2p6. It'd save you writing that out. Okay, there's a couple more things I want to tell you about this chapter. Actually, as it goes into chapter 8, I didn't get to chapter 8. I thought I would, but I spent more time talking about configurations than I thought I would. We will pick up on chapter 8 on Monday. Do you have any questions for me? So I will release chapter 7 quiz today for sure. So check for chapter 7 quiz on Chem 101. It'll be available today after probably 2 p.m. And it won't be due until April 27th. I'll wait on the chapter 8 quiz. If you were a little lost today because you didn't watch the videos from last time, I would encourage you to go back and watch those 3 videos that I posted on Monday about electron configurations, about how we know about the Bohr atom, and what was the other one about? There's 3 of them, but altogether, I don't think they're even 20 minutes altogether. They're 3 short videos. The information on those videos will be on the quiz for chapter 7. You have any questions for me? If not, then I will see all of you on Monday. Some of you I will see on Thursday for lab. You guys have a nice weekend.
Thank you.